In this video, we're going to go through about lenses, converging lens. And if you take a look at the example here from my summary, you should know that this is scenario number 2, where the object is at 2f, and you know that the sharp image will be at 2f, same size, real and inverted. But right now, because the screen is placed further back here, you will get a blur image. How do you see it? It's like all these rays are coming up from the tip of the arrow, but yet the tip of the image is here and over here. It's like a double image. That's why it's a blur image. Now this is not exactly just dual double images. Okay, there are infinite rays. Remember that there are many rays that comes up from here. We only draw the two because there are rules to follow. So basically there are multiple images here. That's why, and it's not it kind of like form a blur image. So what can I do? Okay, basically I'm going to go through 5 methods that you can do to actually get a sharp image on the screen. Okay, the purpose is just get the sharp image, so the size doesn't matter. So on the other hand, if this lens, this screen were to be put here, it's the same thing. You'll see that the tip of the image will appear on 2 points on the screen, so it will be blurred. So you should know that to get a sharp image from theory, you know that the screen has to be put here. All right. So without further ado, let's go through the various methods. So the first method is the easiest. That's to change the position of the screen. As mentioned just now, if your screen is originally here, you will form multiple images resulting in a blur image because they are all overlapping one another but not exactly at the same position. So what you can do is just basically shift the screen forward until this intersection here. That means to say it's very focused, or the tip of the arrow, the object will fall nicely on this point. That will be the tip of the image. So just moving the screen forward, you can get a sharp image. And do know that the image form is real, inverted, and same size, and the application is like a photocopier machine. 100% A4 goes in, A4 come out. Now the second way is to change the lens, and changing the lens, there are 2 types. Let's focus on this one here, using a lens with lower refractive index. That's your N. Now let's recall, previously we have learned that when light is traveling from air, optically less than, to glass, which is similar to your lenses here, optically denser. Let's assume this is the normal and the incident ray hits the point of incident here. This is your angle of incident. Now because the light is traveling into an optically denser medium, it will slow down, the speed will decrease, and you will bend towards the normal. Alright, this is when the refractive index, let's say this refractive index of the glass right now that I'm using is 1.6. But what if I were to change to another glass? Alright, but the angle of incident is still the same. And since the refractive index is now lower, 1.5, the light will still slow down, just like when it's in the glass of refractive index 1.6, but it will slow down lesser. In other words, the speed will still be slightly faster than the black color light ray, and it will bend lesser because the speed is still faster, so you'll bend lesser. This is the case where the refractive index is 1.5. So if you understand the concept, we can apply it to the lenses here. So just now you can treat it as this is a refractive index of 1 point, n equals to 1.6. Now I'm going to change it to a refractive index of 1.5. As mentioned just now, the light will slow down inside the lens, but it will still be faster than when the speed is here, so less bending. Alright, so you will come further down. Just now the focal point will be here. Okay, because it bends here, cuts the principal axis, but now it will bend further away. If it bends further away, this intersection point will be further away from the lens. That's why it is able to form a sharp image on the screen. And if you're wondering, this ray here, because the height and the position of the object doesn't change, so this ray, it remains the same. So basically we are only this ray here will change. Now another thing to take note is, of course, the bending of light will not take place within at the middle of the lens. So if I have to enlarge the lens for you, so as the light ray hits here, this is the normal, the speed slows down, it bends towards the normal, and then this the normal bends away from the normal. That's why you have this direction here. So take note of that. The bending of light, the refraction take place at the air glass boundary. Next is still on changing the lens, but we will keep the refractive index the same type of glass. The only thing we change is the curvature. So we're going to change it to a thinner lens. So if I show you the enlarged version of the lens, assuming this is the fat one and this is the new thinner lens. So if the same incident ray were to hit the air lens boundary, because of the curvature is more steep, okay, this will be your normal perpendicular to the boundary, and then you will bend towards the normal, where this is your I and this is your R. And likewise, the normal is over here and it enters into the air, the speed increases, so you'll bend towards the away from the normal. But if the lens is actually more is thinner, all right, you can see that for the same incident ray, the I will be smaller. This is the normal, so you will bend lesser, and then the normal over here, you will bend away from the normal. So you can roughly get the idea. If this is the optical principal axis, your focal point where it cuts the principal axis here will be further away. The focal point is further, or in other words, it will be a longer focal length. So back to the diagram over here, because there's less bending at the two boundaries here, the intersection point will be further away from the lens, and if it can fall nicely on the screen here, you'll get a sharp image. So that's another way to get a sharp image. Next, we can also change the position of the object. So what can we do? We can basically shift the object nearer to the lens. Now if you can recall the summary that I gave you, there are 4 scenarios. The first one is being when the object is more than 2f and the image that you get will be real inverted smaller. This is the second scenario, and the third scenario is when the object is between f and 2f. All these 3 scenarios, you will get a real and inverted image. All right, and remember the pattern that I told you, the trend, as the object is moved nearer to the lens, the image that you form will get further and further away from the lens, and it will become bigger and bigger, magnified. So this is the trend that you must know. So if you understand that, you know that because right now the intersection is here, if I can shift the object nearer to the lens, all right, this intersection point will fall nicely on the screen that's further back, and you'll get a sharp image. Of course, the image now will be different. This is the third scenario where the object will be magnified, real and inverted. So this is like your projector in the class, but the objective is to get a sharp image, and you can achieve that by shifting the object nearer to the lens. Now let's go through the last way, which is to change the object or the light ray. Now I mean, because the concept of blue light and red light, how will it be refracted when it enters into the glass, all this will be tested in O-level, so it's good to know this. And of course, let's assume that this is the original is a blue object, or you can think it of an luminous object that's emitting blue light or is reflecting the blue light. So the main focus here is the blue light, and this is where you get the intersection here. And if I have to change it to a red object or an object that's emitting red light, so you should know that for red light travel faster than the blue light in the glass. And how do you remember that? Because the wavelength of the red color is greater than the wavelength of the blue. This is something that you should know. And if you can remember, grandma extra underwear lingers in my room. How do you recall? No need to memorize. How do you recall red color light has a longer wavelength? Remember, visible light has 7 colors. How do you know which side is the red? Just recall this: infrared, so the red is here, and the ultraviolet, the violet is here, and therefore the blue is this side. So you know that radio wave has the longest wavelength. That's how you remember. So another thing you should take note is both the blue light and the red light will slow down in the lens, but the red light will still have higher speed than the blue light in the lens. In other words, there will be less bending, as mentioned just now, earlier part in the video. There will be less bending. So that's why this red light will go further down when it cuts the principal axis. In other words, the focal length will be longer, and that's why the intersection can nicely fall on the screen that's further back. Okay, so that's another way to achieve to get a sharp image. Of course, the image now is different. It's red color compared to just now blue color. Alright, so these are the various way, and these are the various concepts that you must know and able to apply. Alright, I hope this video helped you to understand more. Thank you.